Okay, yeah. I started the recording. Okay. So any questions so far? Okay, then, so let me share the screen. Okay. Yeah. So is this screen visible? Hello?
Yes, sir, it is visible.
Okay, yeah, good. So if you try to recollect, in the last week, we started the discussion on the processor, designing of a processor. It basically involves designing the data path and its controller. So we have seen the simpler design, nothing but known to be like a single cycle processor. So it means that all instructions will be executed in one clock cycle, whether the instruction may take a less time or long time. So all of them will be executed in one clock cycle. So the problem with that is that, so the longer instruction or the instruction which that takes more time, so that dictates the clock period or the clock rate and all. So with that, the efficiency, the overall efficiency will come down because there may be simple instructions which are very frequent. They may need less amount of time, but still the few instructions which requires a longer time, so they dictate the clock period. So because of that, the overall efficiency will come down. And so to overcome that, the other alternative will be like the pipeline design, where we have seen that the multiple instructions can run parallelly, where we analyze that each instruction execution will follow a sequence of various stages. So if you can able to properly execute the instructions like in stages by sharing the multiple stages of a pipeline, so that the multiple instructions can able to run parallelly. So with that, the throughput increases, that in turn increases the efficiency and all. So those things we discussed in the last week, and in that context, we also discussed at a very generic phenomena. What are the problems that are involved with the pipeline? As long as the pipeline runs smoothly, like all instructions will follow sequentially one after another, then there won't be any problem. But there are some issues like data hazards where there will be some dependency between the successive instructions. So that creates some issues in the pipelining, like following the pipeline principle. And similarly, in case of conditional jump or conditional branch instructions also, the instruction to be fetched depends upon the branch result and all. So that also creates some problems in smooth running of pipeline. Those are known to be control hazards. Likewise, there are some structural hazards that are due to like hardware constraints or resource constraints and all. The same resource is used by the multiple instructions of multiple stages and all. So then also the issues will be there. So we just gone through that all of them. And now here, from here onwards, we'll see that how those hazards will be overcome. That we'll discuss in the next class mostly. And today we'll try to discuss about what will be the data path in the context of pipeline architecture, and how the controller will be in case of the pipeline architecture and all. So for that, actually, as we have seen that if you look at this diagram, this is like a single path, single cycle data path. And what we have seen is that in that case of pipeline, the single cycle data path where all resources will be engaged by the same instruction. It's throughout its execution. But here in the case of pipeline, we'll try to split this data path into the multiple stages. and then we'll cleverly use these different phases by the multiple various instructions, like the multiple instructions instead of single instruction. So for doing that, so whenever the instruction is passing from one stage to other stage, it has to use the information whatever is acquired or whatever is carried out in the particular stage is required for the next stage. So likewise, when the instruction is moving from one stage to other stage, it requires to pass the information from in the successive stages, one stage to other stage. That applies to for all instructions, for all the stages also. Like when instruction is passing from IF stage to ID stage, then in IF stage the instruction word is fetched from the memory, and that has to be given for the next stage. And in the second stage, for example, the instruction decoding was happened and the control signals were generated and the register operands were fetched. So all this information to be passed to the next stage, execution stage and all. And then in the execution stage, there may be some result will be obtained upon the contents whatever is fetched from the previous stage, and the result will be again that will be passed on to the next stage, whether to store that result in the memory or whether to be write into the register file or whatever. So again, in the data memory, whatever the data that is fetched from that will be passed into the register file or something like that, or you need to write something into the data. So what I mean to say here is that in case of pipeline architecture, so whatever information that is generated in that particular stage is required will be passed on to the next stage. So how do you do that? So here what we are doing is that in case of pipeline architecture, where each stage will be executed in a cycle, in one clock cycle. But here the clock cycle duration is much smaller compared to the earlier, because earlier the clock cycle is required for execution of whole instruction. But here the clock cycle that is required for execution of a particular stage. So obviously the clock period or the duration of the clock cycle will be much smaller compared to the earlier one. And here we'll assume that each phase or each stage will be executed in one clock cycle. So therefore, it means the information will be passed from like one clock cycle to next clock cycle between the adjacent stages and all. So how do you pass that? That means when the whatever the information generated in a clock cycle, that has to be stored and that has to be passed to the next stage in the next clock cycle, right? So that way we need to carry out the information that we need to whatever the information that is generated in a specific stage has to be stored and maybe make it available for the next stage. So for that purpose, what we can do here is that we can use the same data path of a single cycle, but we'll try to split this single cycle data path like with a phased manner or the stage by stage and all, like instruction fetch, whatever the resources that are required. So that will be in the phase one, in the instruction fetch. And for the decoding and fetching the registers and all, whatever the resources that are required, that will be in the stage 2 or in the instruction decoding and the registration fetch stage. And likewise execution stage. So whatever the components, whatever the data path component required, that become. So that way here to pass the information between the stage across the stages and all, we need to store the information and make it available for the following stage. So for that, in between the stages, whatever if we keep the registers known to be pipeline registers and all, and these registers will hold the information whatever is carried out in the stage in the clock cycle, and it's make it available for the next clock cycle. So that way here, if you look at here, the dotted lines here, the vertical lines, so those are the boundaries between the stages. So if you employ a register here where that register holds the information that is generated in the previous stage and make it available for the next stage with respect to clock. That means here whatever is generated here, so that will be stored in a register and then it is make it available for the next clock cycle in this. So likewise at every stage, whatever the vertical lines here, in place of this, if you keep the registers, where the registers will hold the information whatever is generated in a stage, and then so that they will store it and it make it available for the following stage. So if you look at here, this is the way here, the same thing, this diagram is the same as the previous one. And here the registers were placed here at appropriate places at the boundaries of the successive stages and all, and where the registers holds the information, whatever is generated from the stage, and then that information will be used by the following stage. So every clock cycle, the information will be changes and all. The first in the first cycle, whatever is generated, it is stored here, it is placed over here, and in the second generation, in the second cycle, it will be used by the following stage. And then at the end of the second cycle, again, it generates something and it will be placed in the register. So that way, the information generated will be stored in the registers and it is make it available for the following cycle. And here, if you look at here in this diagram, in the previous diagram, here always the information will be generated and it will be passed on to next stage. It's in the forward direction. It is in the from left to right. So, but here most of the paths are from left to right. There are some paths, if you look at this data path, there are some paths which are indicated by blue colored. They are their direction is in the opposite direction. They are from right to left. You can see here, suppose for example, if the instructions that are involved in the right back phase and all. So here, if you look at here, the output will be like one of these two outputs, like whether it's a ALU result or it may be from the extracted from a data memory. So this has to be right back into the register, right? So in that case here, the register file is over here, right? And here the write back here has to be taken place over the register file and all. So it means that the path is again coming from, like you can say, right to left. And similarly, in case of branch instructions also, if you look at here, the address that is generated from the computed from the branch instruction, so that is again passed on to the first stage. So here also, if you look at here, the data that is moving in the opposite direction, whereas the most of the cases data will be moved, data or whatever the information will be moved in the left to right, whereas here these two cases it will be right to left. And because of these two opposite paths, that leads to hazards. Like for example, here the blue line here at the bottom, that is coming in the write back stage, it is the data will be stored back into the register file. So this leads to the hazards, what we already come across, known to be the data hazards and all. Right. So here what is happening here, the instruction in the fifth stage, so that is using the register file for writing purpose. But whereas simultaneously there are instructions that is there in the second stage, so they try to access the register contents. They try to access the register contents for reading purpose, right? So there will be conflict over here and all, like because the same register file will be used by reading and writing purpose, but they are different because here in the fifth stage it tries to write into this one, and here in the second stage the register contents, whatever is there, they are read from that and they will be placed in the register. And similarly here also, if you look at the address part also, here in the normally the PC will be updated for every instruction. That means after the instruction is fetched, then the PC will be prepared for the following instruction, PC plus 4. It's a regular way it used to do that. But in case of branch instructions, the instruction to be fetched is not the PC plus 4. If the branch is taken, if the branch is correct based on the condition checking, if the branch is taken, then the instruction to be fetched may not be the PC plus 4. It will be somewhere else. So therefore here again, because of this one, this is because here the blue line is providing some address, and whereas here the black line is providing the usual, the conventional PC plus 4 address and all. So it has to pick up from one of these two things, and for that that leads to a control hazards and all, like which one has to be picked up. And another thing, the data is moving from back from the previous to the current stage and all. So therefore this leads to, that means here the data is arriving from the memory, and whereas here the data is arriving from the right back into the previous stages, not in the forward stages. So these two leads to different hazards, whereas here this leads to the data is arriving from a memory stage and coming to the fetching stage. So this leads to control hazards. We'll see that. And the data coming from right back to the register stage, that is stage 2 instruction decoding stage. Here this leads to the hazards related to the data hazards and all. We'll see that how these problems can be overcome and what is the additional hardware that is required for this and all. Whereas all other paths, if you look at, they are in the forward direction, then there won't be any issue at all. Whenever the path that is coming in the opposite direction, they leads to complexities, they leads to the complications. Yeah, this is the way you can, as I mentioned, like you have registers are required here. If you look at here, the case of pipeline architectures, the data path will be similar to the single cycle data path, but we are inserting the registers which used to help to pass the information from one stage to other stage and all, right? Okay, now if you look at the, yeah, this pipeline, yeah, that means we are using from the single cycle data path, right? And then we'll see that the single cycle data path, we look at cycle by cycle at the different stages of the pipeline data path, we can look into that. So the way the data path in the case of pipeline architecture can be looked at into two ways. One is that from a single cycle perspective itself, you can able to see that, and from the multi-cycle purpose, we want to see that there are multiple instructions are there in the pipeline. So in a particular cycle, what is the status of various instructions and all, right? At a particular cycle, at a particular clock cycle. So what is the status of various instructions? That means some instruction may be in the execution stage, another instruction may be in the decoding stage, other may be in the write back stage. So all these things you can come to know that by using these different ways of representation. We'll see that what is that later on. And now here, these diagrams, whatever I'm showing here, the path diagrams, they are just stage by stage, like in a different clock cycles for a different instructions, what will be the activity that is taking place, or like which of the data path is used in a particular cycle and all. For example, assuming that you are starting with the load word cycle or a store word cycle and all, the first stage will be like instruction page stage. So therefore, in this total data path, for this load word instruction, so this is the stage that is activated. That means here the PC indicates the address, and then from that address, whatever is the instruction word is there, that is fetched from that, and then it is placed into the register. It tries to place into the register, and here whatever the PC is there, that PC plus 4 will be calculated over here, and that is make it available here to be entered into the PC and all, to be allowed to be replaced by the PC in the next clock cycle. So this is the activity of the clock cycle 1 of a load register, or you can say the instruction fetch stage. So this is the activity that will be takes place. Then coming to the next cycle, where you can say that whatever is the instruction that is available, that is placed, and that is available for this stage. So from this instruction, we'll come to know that what are the register addresses to be fetched, and similarly the same information also will be used by the controller, also part of the information of this instruction word, opcode part, whatever and all. And similarly the sign extension, all this is the part. You can see the highlighted portions corresponds to the resources that are used in the second stage, and then this is the third stage, right? And then this is the fourth stage, and then this is the fifth stage. So in case of a load instruction, all 5 stages will be effective. All 5 stages, the instruction will make use of the resources of all 5 stages, one after another, in a sequential way, right? And here what you note is that actually here this is the 5th cycle of a load word, right? Sorry. Sir, సార్ నేను యా వస్తాను సార్, నేను క్లాస్లో ఉన్నాను. ఓకే సార్. యా ఓకే 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 సార్, నేను వస్తాను. నేను ఏంటండి, నాకు ఆఫ్టర్నూన్ వస్తున్నాను. నేను ఆఫ్టర్నూన్ వస్తాను, కలుస్తాను, మాట్లాడతాను. క్లాస్ జరుగుతుంది. ఓకే, థ్యాంక్ యూ. ఓకే మేడం. Sorry. Okay. So sorry for the interruption. Yeah, this is for the load instruction, and then yeah, here is the problem in case of load instruction. For example, here, because in the case of load instruction, if you look at here, till these 4 stages there won't be any issue at all. But in the case of 5th stage, here you can see that the data path is coming in the reverse direction. It means that in the case of 5th stage, here the content, whatever the memory content, has to be placed into the register file and all. And for that, here both the data but it has to, here the data is arriving from this data path, and then it has to be stored, or it has to be placed into the specific register. But here at this point of a time, there is another register in this stage 2, right? Because now the actual load instruction is the 5th stage. But in pipeline, because immediately the next instruction will be fetched, so that way the remaining stages will be occupied by its following instructions, its preceding, its following instructions, right? So now at the stage 2, there may be some other instruction will be there here and all, right? And now, but here the load instruction want to write something into this register file. And whereas here at the stage 2, the contents of instruction as per the instruction here, the right register address will be different, maybe different. So therefore here we have a complication, here we have a problem that leads to errors and all. So therefore we need to, because here whatever the load instruction or the whatever the data it want to write into that one, the address will be there. It's not now available because the address is available at that time when the load is here in the second stage, right? And now here, but that address will be required at the fifth stage, right? But here at this point of a time, that address is not available. So that's a problem over here and all. So to overcome this problem, thing is that whenever the load instruction is there, at that time, along with the data, whatever you are passing the information, along with this information, you also need to pass the register, the destination register, where to write that particular destination register ID, that 5 bits. So that also need to be passed along with the load instruction as it passing through the different stages and all, right? So it means if you look at here, this will be clearer to you. So here in case of load instruction, so at stage 2, like in case of load instruction, when the address is generated at that time, whatever the destination register was there, so that register address also has to be passed through all these stages. And then at that time, when the fifth stage, that means when the load instruction is at the write back stage, at that time, along with the data, it also need to pass the register number also. It also pass the register number. And then now both the register, now both the data that what to be written and where to be written, that register address, both are available. So therefore, now the load instruction can write into the register properly in the specified register and all, right? Is it clear here? In case of when you're performing the load operation, the write back happens in the fifth stage. So if it is the fifth stage, the actual instruction that is there in the instruction, the decoding stage will be different instruction. And that particular instruction, as per that instruction, that the contents, the register contents are different. So we need to write back into the register whatever is there, whatever the load instruction specifies. So for that purpose, what we are doing is that in that from the along with the load instruction, we need to also we need to capture somehow. We need to the register or destination register ID, whatever is there. So that also has to be carried out along with the load instruction along through all through these stages and all. So that's what you can see here. So whatever is the register was there, destination register, that has to be taken and it has to be passed through all these stages. And then when it comes to the fifth stage, then along with the data, whatever is acquired from the memory, along with the data is in the black line representation, and the address part is also passed to the register file. And now we have both the specific register and the data content, both are available. So with that you can able to write into the register file and all. So this is one thing where you can able to overcome the problem of loads for using the same register file and all. Here the register file will be used by both the load instruction as well as that is a load instruction that is there in the fifth stage, and as well the actual instruction which is there in the second stage. So both will be utilized by the same register file and all. But here the load is used for writing purpose and the second instruction is used for read purpose and all. So that is the reason that actually writing will be done is represented in the first half of the cycle, whereas the reading will be done in the second half, because here the reading will be enabled from beginning. But finally, whatever you are reading at the end of a clock cycle, so that will be the actual one that will be placed in this register and all. So that is the reason that because the read is enabled from beginning onwards, clock cycle beginning. So the same thing will be there appear. And so whatever is there finally at the end of a clock cycle, whatever is available at the read ports, so that will be placed in these registers and all. So that's the purpose where the reading is represented at the second half of a clock cycle for representing the resource and all. And whereas the writing will be done at the beginning, at the beginning of a clock cycle. Okay. Yeah, the same thing here. Earlier, actually, the 5 figures, the previous one, the 5 slides, whatever it shows about load and all. Whereas for storing and all, because load and store, whatever, for all instructions, for the sake, the first 2 stages are remain same, because the fetching is same for all instructions, and the decoding is also same. That means more or less, because the decoding and the corresponding register operands will be fetched, will be ready for the next stage and all. And the other stages will be different. In case of a store information store, where here you can see here the one of the register contents will be passed to the next stage, and because here the store what need to be done, here the address calculation will be done by the ALU, and that gives you the memory address, and then one of the register contents has to be stored in the memory. So these register contents, whatever is here, so that will be passed, because here these register contents are available here itself, and that will be simply had to pass to the this particular pipeline register and all. And now the register contents are available. And at the end of this particular cycle, you have address is available, because the register contents is already available here. And so therefore, just simply we are passing the register, we are placing the register contents, whatever is available here, we just again storing in this particular register. And here in this stage, the address calculation is done, and that address calculation also placed in pipeline register. So the next clock cycle, both the address is available and as well the register contents also available, and you can write into that. You can see that. So this is for the this particular stage. And then coming to the next stage, store, where you have address is taken from this one and as a LU output, and the register contents are already placed in this register. So what are there? So with that you can do that. And in the write back stage, nothing, because the store instruction doesn't have any write back stage, doesn't have any write back operation and all. So therefore, if you look at the data path and all, nothing happens here. This is just, it means that during that particular cycle, the write back stage is empty. Empty means there no operation will be performed and all, nothing will be done, right? So likewise, in other cases also, if you look at here, this is the way the data path used to be in case of pipeline architectures and all, where you place the registers in between the stages, and these registers will be helpful for passing the information that is generated in a particular stage to the next stage in the following cycle and all. As I mentioned, like in case of pipeline architecture, one way to show it, one way to representing is by using the single cycle data path and highlighting the like various stages as and when the instruction is moving from one stage to other stage. So this gives you the like all the different components, everything, connections, paths, everything will be shown here. And there are other way of showing the instruction execution in case of pipeline architecture will be this way, this fashion. So here, if you look at here, the stages are represented by rectangular boxes and all, simply like because rectangular boxes means it's a kind of storage and all, like here in this case it's an instruction memory, and here this is a register file, and then the data memory, and again write back is a register file and all. And this is the ALU symbol is used because it requires 2 inputs perform certain operation and all. And if you look at here, the way the pipeline diagram is shaded, you can see that ALU means it is completely used, whereas the memory portions are the storages and all. So you can use it whether you are using that storage for reading purpose or writing purpose. So based on that, it is appropriately shaded and all, you can able to see, right? And in case of load instruction, for example, you are using a data memory for reading purpose. You are fetching the contents from the data memory, right? And whereas in case of store, store is not here and all. So in that case, where you can able to see that the data memory will be shaded in the first portion, in the initial portion, right? And if you look at here, in case of subtract and add instructions here and all, so there is no work in the data memory, the memory stage and all, because these two will make use of execution stage, and afterwards the output will be stored in the register file. So therefore, if you look at here, these arithmetic instructions and all, you can see that the data memory stage in there, when it is passing through pipeline, in the data memory stage, there is no activity at all. So therefore, you can see that there is nothing was shaded here. It indicates that there is no activity. Simply whatever the result you will get at the end of the execution stage, simply it will be passed on to the next stage without doing anything at all. Right. So by looking at this kind of structure, representation, so one can able to see here, these are the clock cycles. This is the time, you can say that clock cycles, right? Clock cycle 1, 2, 3, and so on. And here, these are the sequence of instructions that are entering into the pipeline. The first instruction that is entering will be load instruction, assuming that it's cycle 1, and it will end up by the clock cycle 5. And immediately in the second cycle, the next instruction will be entered, then the next instruction third. So that way, this particular way of representation will come to know about actually in which cycle. Suppose, for example, if you take a clock cycle 4, for example, so how the resources are occupied, like which of the resources are occupied by what instructions and all, so that you can come to know that. So here you can see that in cycle 4, the load is in the fourth stage, right, and which is in the data memory, and the subtract instruction is in the execution stage, add instruction is in the decoding, instruction decoding, register fetch stage. So that way you can come to know about like what instruction is there at which place and in which clock cycle, or with respect to a clock cycle, what are the, how the resources are occupied by what instructions. So these things will come to know by using this kind of representation and all. And here these like the vertical lines, the vertical boxes, rectangular boxes. So these are the pipeline registers and all. These are the pipeline registers, right? These are the pipeline registers. Okay. This is the same thing, whatever is shown here, and this is a traditional way of just showing the pipeline architecture. The same thing earlier and all, here in place of these stages under the appropriate symbols were placed and all. Here instead actually only the names of the stages are placed over here. Other than that, they remain same. Yeah, and yes, yeah, here this is the same thing. The as I mentioned, like you can have two ways you can represent. One thing is that the previous one where for every cycle will show all the data paths, but in a staggered with the time aligned way. Whereas here in case of single stage case where you can able to see the whole data path and the corresponding the vertical portions corresponds to the corresponding like instruction at that particular stage and all. Right. So then so far we have seen the pipeline data path, like data path in case of pipeline architecture and all. So now we'll see that. So for controlling this data path, how the controller looks like, and how because you can see that in case of here where the controller has to pass the control signals to all the stages and all, because you can see in the different stages where there are different instructions were there, right? Maybe in the stage 4 load instruction may be there, stage 3 maybe the arithmetic instruction may be there, stage 2 maybe some other instruction. So we have different stages. At the different stages we have to pass the appropriate control signals of that particular instruction at that particular stage. And if you look at here, the control signals in the case of pipeline architecture also more or less same, more or less similar, because the only difference here is that these control signals has to be passed to has to be fed to the resources at a specific time, at a specific cycle, right? And otherwise, because we see that the data path with variation from the single cycle to this pipeline data path, both are same, except that here we are inserting the pipeline registers. That is the major change. Other than that, more of the more or less other resources are remain same, right? So therefore, the control lines or the control signals also more or less same, like in case of pipeline architecture also. But we'll see that how this controller has to feed these control signals for various instructions at different stages appropriate correctly, right? We'll see that. So otherwise you see that the control signals which are marked here by blue colored, they are remain same. They are, as you can try to recollect the control signals that were there in your in the single cycle data path and the single cycle architecture, the same thing, the same control signals and all. But we had to, but here the difference is that this control, there the control signals are generated at a time, and all the control signals are given to all the resources on the entire clock cycle, because there is no overlapping of instructions there. That means the instructions will be executed, and after its completion only the next instruction will be fed. So therefore there won't be much issues in the case of controller design. But here simultaneously in the data, this total data path will be occupied by 5 instructions, right? And now the controller has to generate the control signals corresponds to these 5 instructions appropriately, and they have to be placed in the appropriate stages, right? So that way it appears to be difficult, but it is not that difficult. You can able to see that here the pipeline controller is almost similar to or same as the controller for the like single cycle approach, right? The difference here is that these control signals also has to be passed through these pipeline stages, and whenever they are required in that particular pipeline stage, only those control signals will be used, and the remaining control signals will be passed to the further stages and all. So what it means here is that we are using the same controller, and the instruction will be taken as input, the opcode will be taken as input for this controller, and it used to generate 9 or 10 control signals that we have seen, right? In the single cycle path, in the single cycle data path, single cycle processor, we have around 10 10 control lines are there, and these 10 control lines for the whole data path, right? So they will be for this one ALU, and they are also used for data memory. They are also used for write back. So everything. But now here the instruction is executing these control. The instruction will be executed like stage by stage. So in the execution stage, only ALU will be there. So the appropriate control lines, whatever control signals, whatever meant for this execution stage, only those has to be passed on to here, and the remaining control signals has to be, because the remaining control lines are useful when the instruction is in the appropriate stage. When the instruction is in the data memory stage, only those control lines are required, whether to write into the data memory or whether you read from the data memory. Accordingly, corresponding control signals has to be given only in that stage. So here the way the mechanism to implement that will be like at the second stage, the based on the instruction, because in the first stage anyway instruction will be fetched. We don't know about the nature of instruction, and the instruction the second stage where the decoding will be done. That means where the opcode will be taken out from that, and then the controller will generate the appropriate signals for execution of that particular instructions altogether. All the signals will be generated in the stage 2 itself. And now all these signals will be passed on to appropriate stage. That means all these signals are not useful at the stage 2. Stage 2 is just for only the register file, reading the contents. For reading the contents, anyway, no control is required because all the time you can read, right? And only for writing the data into register file, you have a control signal, right? So, but writing will be done not at this point. Writing will be done by load instruction or by the arithmetic instruction only in this stage 5 only. So what I'm saying is that all control lines will be generated at stage 2, but they will be passed to like its pipeline register, right? And then from these, all these signals are available in the pipeline register. IDEX means the pipeline register in the border in between the stages of instruction decoding and execution and all. And here all control lines are available, but here when the next clock cycle, the instruction will be executing the like in the EX stage, will be the third stage in the EX stage. So for this EX stage, and here all the control lines corresponds to all are available here, but here it's in the execution stage. So the signals that are corresponds to execution stage, so they will be passed on to this particular instruction, this particular stage, right? And the remaining control lines, control signals, whatever is there, so they will be simply passed on to the pipeline register of the next stage of the following stage, right? So therefore, whatever the control signals that are required for memory, data memory, and for write back, so they will be simply passed on to the pipeline register just for storing the pipeline register in the next stage. And here, whatever is required for execution stage, so they will be sent to this ALU circuit and its corresponding multiplexers, whatever. So they will be delivered here and all. And the remaining will be simply passed on to here. And then when the instruction pass on to here, the memory stage, data memory stage, and the appropriate control signals corresponds to data memory, so they will be like released, they will be passed on to here and all. And similarly, write back ones, so simply it will be passed on to the next pipeline register because they are not required here and all. So that way here, if you look at here, the controller will be like as similar as the single cycle data path. The only thing is that the control signals will be like they will be propagated through all the stages, and whenever they are required, whichever stage they are meant for, so those control lines will be passed to, they will be used, they will be given to that particular stage. Remaining control signals will be simply percolated through stages and all, percolated through the stages across the stages and. So that way, if, the controller for a pipeline architecture will be not that difficult. It will be easier. Only thing is that it has to pass the control signals through the pipeline registers and all. And here, naming of pipeline registers will be this way, like between the stages, like the first pipeline register will be like in between IF and ID. So IF/ID. That means the whatever the information that is generated IF will be stored into here, and it will be used by the ID stage and all. Likewise, the other ones also. Yeah. Now, if you look at this, is the overall like data path and control data path, and then on top of that one, the control signals also will be added to that. So now if you look at here, you see that in the execution stage, the control lines corresponds to execution, that is ALU operation code, then the like this multiplexer registers and all. So whatever is required, so that will be given over here, right? And then coming to the, for example, in the memory stage, so the controllers require whether it's a memory read or memory write, and then the branch also. Right, so that for the corresponding these control lines will be derived from this one, and the write back will be here. The write back control signal, it means the register write. So it will be there for load and arithmetic instructions and all. So that will be simply pass on to the next pipeline register and all, right? And it will be used here. If you look at here, the write back control signal will be, it is generated over here, right, in stage 2 itself, but it's required for stage 2 only. But it's not at that point of a time, because if suppose, for example, it's load instruction or arithmetic instruction, the decoding will be done in stage 2. But the write back control signal, that is register write control signal, so this will be asserted in its fifth stage, in its write back stage. So therefore, the same thing, the same way that the way the address is passed, the same way here also the controller signals for a write back will be generated over here in stage 2. But they will be, it's not applicable, or it's not really applied at stage 2. It will be applied in stage 5 of the same instruction. So therefore, the control signals will be simply there, just pass on to the stages along with the instruction. So when the instruction reaches to 5th stage, at that time the control signal will be given to this register file and all, right? So, and similarly, you can see the address part also here. So in case of here, the register write will be done by arithmetic instructions and load instruction, right? So in case of load instruction, the register to be written will be like between 15. The register address is available at RT, this one, like in the RT position, like that is 15 to 11 bit numbers. Whereas in case of arithmetic instructions, it is a third register, so the number will be, the register number will be available at 16 to 20 and all, right? 16 to 20. That means in the write back, the register that need to be written will be either available at 11 to 15 bits or 16 to 20. That depends upon what instruction it is. If it is a load instruction, it is the 11 to 15, because 0 to 15 will be like 0 to 15 will be sorry. Not 11, yeah, sorry, if it is 11 to 15, sorry, it is the arithmetic instruction because the third operand, right? And yeah, prior to that will be, you have the like other thing, other like a shift amount will be 5 bits, and the original function code will be like 6 bits, total 11 bits. Whereas in case of load instruction, it's like immediate addressing mode. So the lower 16 bits will be like immediate address, immediate field, like offset and all. And the remaining 16 bits will be like we have 2 registers followed by opcode. So therefore, in case of load, the address will be available at between 16 to 20 bits, whereas in case of arithmetic instructions, the address is available between 11 to 15 and all. So which need to be selected, and that depends upon the instruction. Here, this multiplexer, this can be over here also. This can be over here also. There are, it's like a trade-off and all. Like suppose if you keep a multiplexer over here and all, then at least this pipeline register need not store these 10 bits and all, right? It can store only 5 bits if you keep this multiplexer over here and all. So if you keep this multiplexer over here, then the whatever the controller has to pass the control line here in this stage itself. So that way there will be, you can do it like you can keep this multiplexer over here itself, but that depends upon where to place and all, because each stage all the activities should be completed within a clock cycle. Sometimes if you place more of them here in a particular stage, then the clock cycle may not hold to carry out all the operations, right? So that way here this multiplex results up to us, like it's up to the designer. It can place it over here or here, that doesn't matter. If you place it over here, at least this particular pipeline register can save the 5 bits and all. It need not have stored the both 5 bits are not required and all. Only one of the 5 bits is required, because that information will be known at the decoding stage itself, whether it's a load instruction or it's arithmetic instruction, that will be known here itself. So that way, and then after that these can be passed. And here also you can see that the control signal will be again returned back, right? So this is the overall pipeline data path, architecture's data path, and control signals that are embedded over that. So is it clear? So yeah, actually for this and all, you should be like aware of that. The previous ones, whatever we discussed in the single cycle approach. So almost like this is just continuation of that, but in place of pipelines, the certain things will be differ. So that's what we are highlighting over here. Yeah, the next thing is that actually so far we discussed about see in case of pipeline architecture how the data path looks like, and then how the controller will be, like how the controller will generate the signals and how they will be passed on to the various stages without any issue at all, right? And so now now we'll try to discuss about, so far we discussed when you're discussing about a pipeline architecture at a gross level, we discussed about how the pipeline works and what are the issues in that and all. And now we'll try to see that actually in case of issues in the pipeline like data hazards, control hazards and all, how to handle them. We know that we already discussed that suppose in case of data hazards, it mainly due to the dependency of like successive instructions. So these dependencies you can able to handle in a different ways. One is that by using software, you can do that. It means that by shuffling the instructions or by like moving the instructions like up and down properly, so that the data hazards can be overcome to some extent, but it's not all the time. So in that case, actually this one like the assembler or like the compiler can able to cleverly can do that, can able to like place the instructions appropriately so that the data hazards can be avoided to some extent. That is by using the software approach and all. And other approach is that actually using forwarding approach, that one we have discussed. And the other one is that actually using stalling the pipeline and all. Suppose if there is a hazard, and one way, simple way is that actually if you detect the hazard, simply you stop progressing the pipeline and all. Stop progressing the pipeline and all until the corresponding result is available at a register file. So that is one way to do that. And the other one is that by using the forwarding path. That means instead of placing the registers, waiting till the content will be placed into register file. If the content is available, so you can directly forward to the following instruction and the right position and all. So we'll see those things. Here, these sequence of instructions, if you look at here, you can clearly notice that the first instruction is arithmetic instruction. The result will be placed in the register 2, and the same result is required for the next instruction. That next instruction is also an arithmetic instruction, but it's a logical one. A logical instruction where it requires the same result, whatever is obtained from the previous instruction. But this is there in the register. This also requires. That means here the second instruction requires this operand in its execution stage. And whereas this operand will be given to the register file by this arithmetic instruction only in the write back stage and all. So there is a problem here. That means there is a data inconsistency if you access this particular operand in this instruction and all. Right? So that we have seen. So we can overcome this by using a forwarding. That means here, because the previous instruction computes the result of this subtraction, and it's not placed in register, but the result is available at its execution stage output and all. And the next instruction execution starts in the next cycle. So, but the result is already available, but that's not placed in the register, desired register and all. So one way is that since it's already available, so therefore you can directly forward that result to the input of the execution stage of this particular instruction. That's known to be forwarding. And how do you detect that forwarding? Will be like you can, yeah, suppose these are the sequence of instructions. And if you place them in this particular representation, you can see that. You can see this is the arithmetic instruction. And here the result is available. And the next instruction is and here this is the execution stage of and. This requires the the input from this actually, right? And but this input is available only in this stage, only in the cycle 5. Only in the cycle 5 only this register is available. But now in the cycle 4 itself we require that one. But the result is indirectly it's available here. The result, the same result, whatever to be placed in this register, it's available here. So you can forward them directly. So for that, what is required is that first of all, we need to identify that yeah, here there is a data hazard is there and all. It means whatever the content available here is also required the input to this particular stage. So somehow we need to identify this. Once you identify that, then you can able to do the forwarding and all. That means instead of accessing the register operand, you can directly feed the output of this one as input to this one. You can do that. And likewise, in this particular sequence, we have 2 times at the 2 places you require the forwarding and all to avoid the stalls. To avoid the stalls, you require 2 places you require the forwarding. Whereas in the next instruction R also, where this also requires the register 2 as one of the operand for its execution and all. But even at this stage also, it's not write back is not available because at this stage means here by that time the contents are already there in this register, should be there in the register. But here at this stage, only the register writing will be taking place, right? Register writing will be taking place, but it's not there in this pipeline register. So therefore here also the desired contents are not available. So therefore here also it requires a forwarding and all, right? So that way you need to detect that where the forwarding is required, and then accordingly you can able to forward the data from different places to the execution stage and all, right? And here for other instructions not required. For example, add here also requires the operand of register 2, but this is safer. This is safer because here at this because here this add the execution stage in the clock cycle 6. But clock cycle 5 itself we are writing into the register file. So therefore, in a clock cycle 6, the actual content is available here. The desired content is available. So there is no need for forwarding for this add. Similarly, store and forward, it's pretty straightforward. There is nothing, no forwarding is required because here it has to be placed into the memory and all. So by that time it's already there much before head itself it's there. So the last 2 instructions doesn't require any forwarding, nothing, no problem at all. But these 2, the second and third instruction and or, they require the forwarding and all. We'll see that in the next class, tomorrow's class. We'll discuss about how to detect this data hazard. That means when you require forwarding or whether forwarding is possible or not. So how to detect that forwarding and what is the detecting circuit and how you can able to forward it. Right. So those things we'll discuss in the next class and all. So we'll stop here at this point. Okay. So, okay. So let me stop recording.